So here I'm explaining to you how we're going to interpret phylogenetic trees. Or the interpretation comes from these two nodes. They come from this ancestor, so they're the two most closely related. If this branch had a number attached to it, then that would mean, for example, that here we have the most recent common ancestor. That's the root that generated this guy, which is the ancestor to these. So oftentimes we only have sequence for these. And let's say that there is this root here, and then see how this ancestor of these guys. Yeah, oh my goodness. Yes, thank you. So here, so these guys are the sequences we have, and this here is the root, and this ancestor to this tree is closer to the root than this one. See that? So this branch or this edge is longer than this edge. And it could be just style, in which case this would be something called a cladogram. You will see that in another slide. But if there was a number next to these branches, then that would imply that the length actually is telling you that this resembles the ancestor more than this resembles this ancestor. So these two would be more closely related than these two. So, but without a number, without a scale anywhere, then we cannot say that that's what's happening. All right, so all the stuff that is labeled in green here is explaining what is in each of these parts. So, as I said, the terminal nodes, which are the leaves, they are stuff that we either have now or that are extinct, but we have the DNA sequence or the amino acid sequence, whatever it is you're comparing. Most times it's DNA sequence because it preserves better than protein over time. And if you're gonna take sample from something that's already dead, I don't know how much protein sequence you can get. And then here the nodes. So these would be speciation events. So if these guys are different species, then you could say, okay, here was some ancestor species to these. Or it could be gene duplication events, which I was showing to you how then that's how you'd get the paralogs. So let's say you have maybe a histone ancestor in here, and you have 3 versions. So of that histone 1, 2, 3, let's say. Then this is showing that there was a gene duplication and then there are mutations, and now you have different versions of the histone. In that case, this would be a gene duplication event, not a speciation event. Okay, so here's, I'm telling you again, the branch may or may not convey information of how closely related this and this are. The root is, we can call it either the most recent common ancestor or the last universal common ancestor, which would be like the very thing that originated all life. But normally we refer to this one, most recent common ancestor. All right, so, and you can use both of them, but more often you see this one. This sounds very ambitious. It's just a cuter acronym, right? Somebody's name, but it's more ambitious. Okay, so I told you that I wanted to know why some branches are called fully resolved, others not. We say that this node here has 3 branches. And you're like, what? I only see 2. And I'm like, no, the incoming branch is also counted in here. So there's the incoming branch, and then the outbound branches. So that node has 3 branches. We call that fully resolved. This one here is not fully resolved because it has the incoming, the 2 outbound, but then there is a 3rd outbound. So it has more than 3 branches. So we say that it's not fully resolved because when species diverge, let's say that this is a speciation event, normally one species, so this is what normally happens, one species will diverge into 2. It won't be one ancestor diverging into 3. It could happen, but we understand that biologists think that this is happens much more often, that one ancestor species will give rise to two different species, not three. So I tell you in here that that's why evolution rarely gives rise to more than two species in a single speciation event. That's why you're like, maybe we're missing an ancestor to this guy here, so there will be like another partition. So, or maybe from over here, and then that would resolve that tree. All right, so now you can either use your pointer, I don't know if you can use the pointer, to point to some bird. So there are those two trees. Let's see, let's start with the tree B. What's the most recent common ancestor? Oh, yeah, I see. So you're like, okay, something from here. That's true. I was thinking this guy, but I don't know either why they even drew this other one. So they label this guy as the root. But yeah, maybe here. That's a good point. I didn't think of that. So this one is easier, right? So which I was like, no, no doubt, is this one. Okay, or this one. But in any case, we know that whatever this is gave rise to this, and then this guy mutated and okay, changed just the color, became yellow, and then it just changed the wing length. So remember that the phylogenetic tree can also be looking at morphology. That's how it started. And in here, okay, it kept the color but changed the wing length. So we know that this is the ancestor one. Now, how about this one on the left? Yeah, I know it's tempting, right? So let's see. This guy became brown and lost weight too. Or anyway, and this from here to here, the wing was longer. You could think maybe this is the root. Let's see. Could it have been that this one is the root? So you go like started like this, and there was some mutation. Now you have this guy, and then this mutated into these two, and then this mutated into this two. And I like this is resolved. They're always resolved. And then this mutated into those two, and this other one mutated into those two. So that actually would be another possible interpretation of this tree here. You could say, how about if this one is the ancestor to all, and then he lost the crest, whatever this is called in English, and then became that. So mostly, I wanted to be driven crazy trying to figure out which way this went and not get anywhere, because this tree on the left is an unrooted tree. We don't know which one is the ancestor one. We wanted to pick, if I compare it to the one on the right, then I am like, oh, it's the brown dude, so it's this one. No, that guy's not in here. So I don't know. In this tree here, it's the same case as the Little Red Riding Hood. We don't know which one is the oldest one that diverged into the newer ones. So unrooted and rooted. Got it? All right. So here's I'm explaining that the unrooted, it shows how they are related to each other, but there is no direction. You can't say, this gave rise to this. We're tempted because it goes down, because that's how we read. But maybe this one gave rise to this three. This part would be unresolved. So we don't know. But the rooted, then these are all inferences, right? This is how we understand. We don't actually know anything. These are all educated guesses. So let me go back just a moment. Because we like looking at trees like this rather than like this, even though this makes more assumptions that may not be true, I don't know, we just like to know what gave rise to what. So people like rooting trees, which maybe we are leading people to think something is true when it's not. But it's not just like, let me close my eyes and go like, this one. No, there are methods for rooting a tree. So here's what we do. What you do is you see you compare these three entities, and then you see which three or which is the most different of all, and you call that one an outgroup. And then your outgroup helps you root your tree. So like in this example here, okay, the birds are labeled with letters. Which one is the outgroup on here? Right. So yeah, bird G, because that is the most different. So we make that the outgroup, and then when we have information, either the sequence or morphology, then we see, okay, this is my most different one. Now, of all these guys, which is the next one that is more closely resemble my outgroup? And that is how we root a tree. So here I'm explaining what I just said. So it is, you find the most different one and make that an outgroup, and then you go backwards. What's now the most similar to this? So find the most different, and then after you found the most different, you found which one of these is the most similar to the most different. Okay, so here is something fun. You can put on the chat. I'll let you read these guys, and I'm going to actually make a poll.